The James Webb Space Telescope has been focusing on the smallest objects for NASA's answers about the universe. The new eye above has been tracking down dazzling pictures of stars, gigantic designs, and planets. In any case, at last, something unexpected has been found. Something so huge it could shake the very spines of all that we understand. It has scientists pondering its implications and determining whether it might cause the farthest requirement of everything. Join us as we explore how the latest discoveries of the James Webb Space Telescope could demolish our comprehension of the universe as it existed. Explore the universe's outer limits with us. When talking about the observable universe, the visible universe seems like a window through which we can look at the magnitude that is beyond the scope of the known universe. It encompasses all that we can presently perceive, measure, and investigate using our space probes and telescopes. It's a collection of galaxies, stars, and heavenly bodies at our fingertips. Regardless, the observable universe is just a small part of the entire universe. Envision it as a slice cut from a tremendous, immense pie that we're able to study and comprehend, while the universe's total area and shape remain a mystery. Scientists estimate the width of our observable universe to be approximately 93 billion light-years. A light-year measures the distance that the speediest thing in the universe, light, travels approximately 5.88 trillion miles or 9.46 trillion kilometers per year. So, when we discuss the observable universe's breadth being 93 billion light-years, we're talking about a huge distance. Around 13.8 billion years ago, the universe burst into existence in an impossible-to-understand impact, an event known as the Big Bang. Since that tremendous birth, the universe has not only been growing, but has also been expanding at a bafflingly rapid pace. Forces like the mysterious dark energy seem to be accelerating this speed, stretching the boundaries of the universe further and further apart. As the universe expanded, matter began to clump together under the influence of gravity. This force joined particles, birthing stunning structures, stars, massive galaxies, and eventually planets like our own Earth. Picture the universe passing by as these colossal structures formed, evolving into unique yet constantly growing oddities. Despite its vast size, the universe is incredibly empty. If we were to shrink our entire solar system to the size of a quarter, there would still be approximately the length of 2 soccer fields between us and the nearest star. This expansiveness extends within our own galaxy, the Milky Way, which is just one among the billions that can be seen in the universe, giving us a sense of the sheer size of infinite space. Now, you may ask, why can't we simply see everything that exists in the universe? There are several reasons for this restriction. Most essentially, even the fastest thing known to humanity, light, still takes time to travel. This means that when we look at distant objects in space, we are essentially studying the past. The further away an object is, the more time its light has taken to reach us. It's like looking through a vast time machine, unrolling the history of our universe as we observe galaxies millions, or even billions, of light years away. Additionally, because the universe is expanding, new places are emerging. Imagine the outer layer of an expanding balloon. As the balloon inflates, the spots on its surface move farther apart. This same principle applies to galaxies in the universe. They drift apart as space itself expands. This expansion stretches the light sent from distant objects, causing a phenomenon known as redshift. Essentially, the wavelengths of light stretch as objects move away, shifting toward longer wavelengths, often appearing reddish-colored. Considering factors like light travel time, the expansion of space, and the universe's constant advancement, it should come as no surprise that we haven't yet fully seen all that the universe has to offer. Even with our advanced telescopes and technology, our view is still restricted by these key properties of the universe. The quest to understand the potential edge or limits of the universe has captivated the thoughts of people across many disciplines. While definitive answers remain elusive, 3 popular theories have emerged, each offering intriguing perspectives on the universe's vastness. 1. Infinite space theory. This theory suggests that the universe expands infinitely with no discernible edge. It aligns with the cosmological principle, which states that the universe is isotropic and appears uniform from any vantage point. If this principle holds, it implies that the universe has no boundary and continues expanding infinitely in every direction. 2. Finite yet boundless theory. This theory proposes that while the universe may be finite, it lacks a clear edge. It might resemble a vast circle or a warped space, similar to Earth. In this scenario, if one were to travel infinitely in any direction, they would eventually return to their starting point, much like circumnavigating Earth. 3. Multiverse hypothesis. This fascinating theory suggests that our universe is just one of countless others. Imagine an infinite number of parallel universes, each existing with its own set of physical laws, constants, and properties. These universes may be entirely separate from one another, functioning independently, or they could be interconnected by intricate systems, forming a vast and complex multiverse. The James Webb Space Telescope, JWST, stands as a symbol of potential, illuminating the mysteries that lie at the universe's beginnings. This incredible instrument has an unmatched capacity to decipher the baffling aspects of our universe's past, allowing us to see much further than was previously possible. The JWST is a marvel of technological design, specifically built to observe the universe with remarkable precision. Its advanced capabilities enable us to see beyond what was once imaginable, back to the very beginning of the universe. A groundbreaking study published in the renowned journal Nature revealed the first-ever discovery of 6 enormous galaxies that formed between 500 and 700 million years after the Big Bang. Astonishingly, these ancient galaxies are far larger than expected for their early existence, challenging prevailing theories about galaxy formation and development in the early universe. What is truly remarkable is the sophistication of these ancient galaxies, which defy the assumption that galaxies form slowly over time. These massive galaxies exhibit a degree of complexity similar to our 13-billion-year-old Milky Way galaxy. The sheer number of stars within these colossal behemoths exceeds expectations, with each galaxy boasting a total mass significantly greater than our Sun strikingly. One of these galaxies may even possess a mass 100 times greater than our Sun, surpassing the immense size of our Milky Way. The JWST's unmatched ability to explore hidden corners of the universe is based on its use of infrared light, an invisible range to the naked eye. This remarkable power enables the telescope to capture the faint emissions of ancient stars and galaxies, revealing immense remnants that have endured for billions of years. Essentially, the JWST acts as a time machine, returning our vision to the universe's earliest centuries and offering a captivating glimpse into how it appeared roughly 13.5 billion years ago. The continuous discovery of these. The observable universe, while vast, represents only a fraction of the entirety of existence. Its boundaries are defined by the distance that light has traveled since the Big Bang, roughly 13.8 billion years ago. However, due to the universe's continuous expansion, this distance is far greater than 13.8 billion light-years, stretching to approximately 93 billion light-years across. Beyond this boundary lies the unobservable universe, regions of space so distant that their light has yet to reach us and perhaps never will. This limitation stems from the speed of light, which, though the fastest thing in the universe, is finite. Light from the most distant galaxies began its journey billions of years ago, long before Earth or even our solar system existed. When we observe these galaxies, we see them not as they are now, but as they were in the distant past, snapshots frozen in time. The farther we look, the older the light and the further back in time we peer. The James Webb Space Telescope's unprecedented infrared capabilities allow it to see deeper into this ancient light, capturing images of galaxies that formed shortly after the Big Bang. However, the universe's expansion complicates this process. As space stretches, it carries galaxies farther apart, causing their light to shift toward longer, redder wavelengths, a phenomenon known as redshift. This effect not only makes distant galaxies appear redder, but also stretches the light beyond the range of visible wavelengths. The JWST's infrared instruments are designed to detect these faint, stretched wavelengths, allowing scientists to see galaxies that are invisible to optical telescopes like the Hubble Space Telescope. Yet, even with this advanced technology, there remains a limit to what we can observe. This limit, known as the cosmic light horizon, marks the maximum distance from which light has had time to reach us since the beginning of the universe. Beyond this horizon lies a realm forever beyond our reach, unless future breakthroughs in physics reveal new ways to probe the cosmos. The recent discovery of 6 massive galaxies challenges our understanding of this cosmic timeline. Conventional models suggest that galaxies in the early universe should have been small, faint, and relatively simple, gradually growing larger and more complex over billions of years. Yet, the galaxies observed by the JWST are astonishingly large, bright, and mature, appearing far too advanced for their age. Their masses are comparable to, or even greater than the Milky Way, despite existing less than 1 billion years after the Big Bang. This discovery has forced astronomers to reconsider fundamental assumptions about how galaxies form and evolve. One possibility is that star formation in the early universe was far more efficient than previously thought, allowing galaxies to grow rapidly in a short time. Another theory suggests that dark matter, the invisible substance that makes up most of the universe's mass, played a crucial role in accelerating galaxy formation. Alternatively, these massive galaxies might be the result of early mergers, collisions and mergers between smaller galaxies that combine their stars and gas to form larger structures. However, the sheer size and maturity of these galaxies present a puzzle that cannot be easily explained. Their existence suggests that the universe's earliest epochs may have been more dynamic and chaotic than current models predict. If galaxies formed and evolved more quickly than expected, it could imply that our understanding of the universe's initial conditions, its density, temperature, and composition, needs to be revised. Moreover, the discovery raises questions about the role of dark energy in the universe's expansion. Dark energy, the mysterious force driving the accelerated expansion of the universe, may have influenced the growth and distribution of galaxies in ways that scientists are only beginning to understand. If dark energy was stronger or behaved differently in the past, it could have affected how quickly galaxies formed and how their structures evolved over time. As astronomers analyze more data from the JWST, they hope to uncover additional clues about these ancient galaxies and the conditions that shaped them. Future observations will focus on measuring the galaxy's chemical composition, star formation rates, and internal structures to determine how they compare to modern galaxies. By studying their light at different wavelengths, scientists can piece together a more detailed picture of how these cosmic giants formed and evolved during the universe's infancy. The implications of these discoveries extend beyond galaxy formation, potentially reshaping our understanding of the universe's fundamental properties. If galaxies formed more rapidly and grew larger than expected, it may suggest that the early universe was more densely packed with matter, or that the laws of physics operated slightly differently in its earliest moments. Such findings could prompt revisions to key cosmological theories, including the Standard Model of Cosmology, which describes the universe's structure and evolution. Additionally, the discovery of these massive galaxies raises questions about the ultimate fate of the universe. If galaxies can grow so quickly, they may also consume their available gas and dust more rapidly, potentially limiting their long-term growth and star formation. Over billions of years, this could lead to a universe dominated by large, aging galaxies with fewer new stars being born. Alternatively, if dark energy continues to accelerate the expansion of space, galaxies may become increasingly isolated from one another, drifting apart until they vanish beyond the cosmic horizon. Despite these uncertainties, The James Webb Space Telescope's discoveries represent a monumental leap forward in our quest to understand the cosmos. By capturing light from galaxies that existed when the universe was still in its infancy, the JWST is providing an unprecedented glimpse into our cosmic origins. Each new image and data set brings us closer to answering some of the universe's most profound questions. How did galaxies form and evolve? What role did dark matter and dark energy play in shaping the cosmos? And what lies beyond the observable universe, hidden beyond the reach of our telescopes? As the JWST continues its mission, astronomers anticipate even more groundbreaking discoveries that will challenge our understanding of the universe's past, present, and future. From detecting the first stars and galaxies to studying distant planets and searching for signs of life, this remarkable telescope is poised to revolutionize our view of the cosmos for generations to come. In the grand tapestry of the universe, each discovery adds another thread, weaving together a story that began with the Big Bang and continues to unfold with every photon of light that reaches our telescopes. The journey is far from over, and as we peer deeper into the cosmos, we may yet uncover secrets that will forever change our understanding of existence itself. Everything in the universe that can be observed at the moment is detectable using telescopes and space probes, including galaxies, stars, and other celestial bodies. However, it's only a small portion of the entire universe. According to scientists, the width of our observable universe is estimated to be around 93 billion light-years. A light-year measures the distance light travels, which is approximately 5.88 trillion miles annually. Around 13.8 billion years ago, the universe began with the Big Bang, a massive explosion that sparked the vast expansion that followed. The universe has progressed and accelerated, driven by mysterious forces like dark matter, which started to coalesce under gravity, forming stars, planets, and eventually galaxies. Earth is shaped by this ongoing process. The universe's immense size allows us to observe only a fraction of its infinite complexity. Even with this expansion, much of the universe remains dark and empty. Despite advancements like the James Webb Space Telescope, JWST, vast portions of the universe remain out of reach. Still, its discoveries continue to alter our perception by providing a glimpse into the amazing wonders that lie just beyond our sight. Space continues to awe and inspire us. With every new observation, we are gradually assembling a more complex understanding of the universe's history and future. The JWST is a tool that could forever transform how we think about space, time, and the very nature of our existence. The repercussions of the JWST extend beyond new discoveries. Its observations challenge the very foundation of modern cosmology. If, at this early stage, massive galaxies exist, it forces us to reconsider current galaxy formation models. For decades, scientists have adhered to the idea that galaxies evolved gradually, beginning as small, dense clusters of gas and dust that slowly grew over billions of years. The detection of enormous galaxies formed within the first 100 million years after the Big Bang present a paradox that doesn't align with this slow evolution. This revelation raises new questions about galaxy formation. How did large, complex galaxies form so rapidly after the universe was created? What forces enabled such rapid star formation and galaxy development on an enormous scale? These questions challenge our current understanding of the early universe and push the limits of physics, especially concerning the behavior of dark matter and dark energy during the universe's formative years. The discoveries made by the JWST have the potential to fundamentally alter our understanding of the cosmos. Its capacity to observe distant and ancient galaxies opens new opportunities for cosmologists to explore the universe's structure and evolution. Operating in the infrared spectrum, the JWST can peer deeper into space than ever before. This capability is crucial because it allows the telescope to observe galaxies so distant that their light has been redshifted into wavelengths that other telescopes cannot detect. By capturing these faint signals, The JWST enables researchers to investigate the universe as it existed billions of years ago. One of the most intriguing aspects of the JWST's findings is the detection of galaxies that formed just a few 100 million years after the Big Bang, a period known as the cosmic dawn. These early galaxies appear more evolved than initially expected, with many exhibiting features assumed to develop over much longer periods. Such galaxies are surprising not only because of their size, but also due to their rapid star formation rates. These observations challenge the widely accepted model of galaxy formation, which suggests that galaxies expanded gradually over billions of years. Instead, the data hints that galaxies may have formed in a far more dynamic and accelerated fashion than previously thought. The rapid formation of massive galaxies so early in the universe's history has sparked intense debate. Some researchers propose that the unique conditions of the early universe, such as the high density of matter, the role of dark matter, and the influence of extremely large black holes, may have contributed to this accelerated growth. Others suggest that our understanding of dark energy and its impact on the universe's expansion might be incomplete, factors that could have influenced the development of cosmic structures. These questions are central not only to understanding galaxy formation, but also to grasping the fundamental forces that shaped the universe in its infancy. The JWST's revelations are also prompting scientists to rethink star formation. Traditionally, the early stages of star formation have been considered a gradual process. However, the JWST's ability to detect distant stars suggests that some stars may have formed much more quickly than expected, possibly under circumstances not yet fully understood. This discovery has significant implications for our understanding of stellar populations and their role in galaxy formation. The interactions between these stars and their eventual deaths in supernovae may have played a pivotal role in enriching the universe with heavier elements. In addition to providing a window into the past, these distant galaxies raise questions about the future of the universe. As the JWST continues to unveil more specific data, scientists will gain greater insight into the fate of galaxies, stars, and the universe as a whole. Its observations of distant interactions between galaxies will shed light on how galaxies evolve and interact over cosmic timescales, offering clues about the universe's long-term future. With its sophisticated technology and unparalleled reach, the JWST stands as a tool that will continue to expand our comprehension of the universe, testing conventional theories and guiding new lines of inquiry for future generations.